Recording in progress.
Hi guys, and welcome to today's lecture. Today is September 29th. I think we are still in week 7. This week is kind of light because we just came off of an exam last week. So in terms of assignments, we really don't have a lot other than the fact that we're closing actually we're in the middle of the solar system. So we started with the moon, Earth's moon, and we went through it and we saw basically how its properties and the peculiarity about it, the fact that it's kind of an odd object, and we learned about its surface and history and everything else. And it serves actually another object in the inner solar system. Sometimes it could be classified as a big object, and it is as a big object on its own, just with the other 4 basically, namely Venus, Earth, and also Mercury and Mars. So it's really a big object. So it was of an interest to itself. As I was saying last time, basically, we wanted to study some of the stuff in the solar system in general, whether we're talking about the inner planets or outer planets. Venus stands out for a lot of reasons. One of them is the fact that it is similar in every which way almost to the Earth in terms of gravity, in terms of size, and in terms of mass. So it's really similar to the Earth. But that's probably the extent to which the similarities end, because every other way also it's different than the Earth. For one thing, it has a big, much thicker atmosphere than the Earth does. As a matter of fact, if you go and look at it tonight, you will see that it's a super bright object. It's the second brightest object in the night sky after the moon. It's the third brightest brightest object in the sky, period. After the sun, then the moon, then Venus comes in. So Venus is a big object, and it really was an object of interest for a lot of cultures, whether in South America or other places also around the world. And it was believed in the old days, at least at some point, that it was 2 different stars, because you could see it sometimes in the morning and sometimes in the evening. It turns out at the end that people recognized it was the same object. It was called in some places the morning star or the evening star. It comes either before the sun in the morning or sets after the sun in the evening, just as Mercury does, with the exception that Mercury follows up closer to the sun than Venus does. Again, because Mercury is a lot closer to the sun than what Venus does. So this is basically some of the general properties of the planet. The planet itself, I mean, at least in the old literature, was thought to be probably inhabited. Basically, it has a living organism in it, and that was basically blown completely out of the way because of the fact that the conditions that are on the surface. We had a lander, the Russians did, at least in the 1970s, called Venera. And they actually had 2 of them. One of them lasted a little longer than the other one. And it basically sent back information about the conditions on the surface that are completely unbearable. No life, at least the carbon-based life that we know of, can live at least in those conditions in terms of pressure. In terms of suffocating atmosphere, remember it's mainly carbon dioxide. So it's not really something that you can breathe. And it also contains huge quantities of sulfuric acid. As a matter of fact, it drains sulfuric acid. If you were on the surface actually of Venus, you couldn't really see the sun through the thick atmosphere. I mean, you probably will see a haze, complete haze, because extremely thick atmosphere that you are going to be subject to. That is provided you could stand in there and see something, okay? So those are the conditions of the planet. The temperature there can reach hundreds of degrees Celsius, temperatures that melt at least lead. So these are extreme high temperatures. When we send probes to other planets, when we go, for example, when we send stuff to the moon or Mars, or even on the surface of Titan, when we had a lander in there, usually we're dealing with the conditions where electronics can basically at least live long enough so that they can send us data. But most of the chips nowadays, they are using the semiconductors, and semiconductors cannot really be used beyond 150 degrees Celsius. So the temperature surface there is about 400 and something degrees Celsius. So no electronics is going to survive under those conditions. It's not just living organisms, but even man-made missions and lander on that planet is not really possible. So there is a lot of things that are going against it. I mean, it's really a terrible place to be. But it should not have been. That's really the biggest question. The biggest thing in here is it could not have been that way. So why in the world did it go that way? Why did it go in this extreme opposite side of what the Earth did? Similar in size, formed in the same region, had been exposed to the same conditions, yet one of them now is completely uninhabitable. I mean, you cannot really have living organisms in it, and one of them that is actually thriving with life on it, namely Earth does. So this is basically where the interest into this topic is. So let me share with you the screen. Obviously, we would want to learn a lot about it as a planet on its own, but we want to know also what kind of things that could basically go wrong for our own planet. I mean, what happened to Venus? Could it happen on Earth? And the answer to that, in a nutshell, yes, absolutely yes. And that is really the thing that we really have to safeguard in here. We really have to work very hard as life on this planet to make sure that life will continue, at least to the extent that we can. Okay. So the atmosphere on Venus, as I was saying, it's a super thick atmosphere. The surface pressure on Venus is 92 times the atmospheric pressure here on Earth. If you were, I mean, if wherever you are right now, you are under pressure of about 100,000 pascals. So you're saying, what is 100,000 pascal? It's 100,000 newtons per square meter. Square meter is probably, this is 1 meter, that's slightly more than that. This is about 1 meter. And another 1 meter on this square, okay, there is 100,000 newtons. And you're wondering, what is 100,000 newtons? That's 10,000 kilograms, basically, on top of that, of air. So to give you an analogy, if you see a semi-truck, basically, fully loaded, that's about it. That's how much mass is sitting in here. So in other words, could you lift a truck fully loaded? And I don't mean a pickup truck. I mean a big one of those 18-wheelers. Obviously, you say, no, I can't, because unless you are really, I don't know, you have to be an exception to be able to do that. You say no, but that's exactly what you're doing right now. You're carrying that much load on your shoulders. But even that is not what Venus is. If you are on the surface of Venus, you're going to experience almost 100 times as much pressure as you experience here on Earth. And those are conditions by themselves, they're unbearable. So you cannot, I mean, you're going to be crushed. So the surface of Venus has tremendous pressure on its surface. And I always draw analogy at this point, because we're not going to stop at it when we do, because we're going to move on to the outer planets and the outer objects in the moons, basically. I draw comparisons with Mars. Mars is actually, its surface temperature, surface pressure, excuse me, is about 100th that of the Earth. So you have two extremes. You have one that is super, super thick atmosphere, tremendous pressure is about 100 times as much. And you have another surface in here, in the case of Mars, that is 100. So the Earth is sitting in the middle, literally speaking. I mean, it's sitting in the middle, but also its pressure is really somewhere in the middle. So you go from a place where you're going to be crushed under the pressure of the atmosphere to a place where you're going to basically feel like you're going to expand. You're going to explode, if you wish, from a place that you're going to implode to a place that are going to explode. And here is the Earth conditions that are suitable for life. Okay. At least life as we know it, and I use the word life as we know it because if probably there is life somewhere else, they would probably look at the conditions on the Earth and they would say that the Earth conditions are not suitable for life as we know it. They would know it, not us. But at least we are conditions to this condition in here, so we know that those two are two extremes in terms of pressure. Now, There is a similarity, though, between the two atmospheres, between Venus and Mars, and that is in the composition. They are both mainly carbon dioxide. Unlike the atmosphere here on the Earth, which is mainly nitrogen. I mean, it has good proportion of oxygen, about 20%, but it's mainly really nitrogen. Which brings me to another moon in the solar system that has similarities. I'm probably going to talk about that down the road, namely Titan. The atmospheric pressure on Titan is slightly higher than that of the Earth. As a matter of fact, if you were to go to Titan and stand on its surface, you should be able to support the pressure on that surface, on that moon, in terms of pressure. And the composition of the atmosphere is also mainly nitrogen. Doesn't have enough oxygen, though, but it has mainly nitrogen. So there is two objects that are similar, namely Earth and Titan. And then you have two objects that are completely dissimilar in terms of pressure, but also similar in terms of composition, namely Mars and Venus. So these are some of the objects that we have in the solar system that are of interest. So again, what we think happened to Venus is that it's really went through a greenhouse effect, and that greenhouse effect went to a complete extreme. Right now, basically, it's stable, but that stability is at a very, very worse condition. So let me explain what's going on. If you happen to sit in a car, okay, even with some of the windows a little bit open, you will notice that it's hotter in the summer than outside. Okay, why? Because here is what's going on. You have light that goes through the windows into the car. That light comes in all wavelengths. It comes in all kinds of colors, basically, of the spectrum, including the long wavelength like red, and including the short wavelength like blue. And as a matter of fact, it comes in other ranges also, frequencies that we can see. The point being in here is those are the main range really for the visible light that come from the sun, at least for us in here on Earth. So what happened in here is that radiation goes in, it's absorbed by your atoms, absorbed by the atom of the seats, the car seats, the car wheels, and all of the other things. They heat up. Why they heat up? Because they absorb energy. So they gain more energy. So its atoms and its molecules start to move faster and faster. And when they do in this case is they re-emit the energy, the radiation. But they don't emit it back in the same frequencies that they receive it. They emit mainly in the infrared. That is basically what the color that is. If you're not too familiar with this phenomenon, you probably heard of the goggles that are used by the military or actually the police at night and things like that, or the hunters actually when they go hunting at night for deer or for game in general. So they use goggles, okay, and those goggles they're for night vision. So what that is that instead of using light to see stuff, which is the visible light that we use, they use the infrared. So an infrared object an object that has temperature will emit radiation that is in the infrared range. As a matter of fact, if you put the goggles on, you can see the hotter parts of your hand. For example, when you press your hand palm on the table or something, you see the imprint in there, at least temperature places that are hotter than others. So that is similar, okay? That is similar in a sense that the radiation that is emitted back is in that range, the infrared. Well, the glass is not transparent to that kind of radiation, at least for the most part is not. So what happened in this case, the radiation bounces back to the inside of the car, and it's trapped in there. So here is the thing. You have an influx of energy, but the outward amount is less than what came in. So at the end, you have total increase and net increase in the energy inside. So this is probably what happened to Venus in its past. So this is what's going on. So probably it had an atmosphere, and it did because of similar conditions that led to its atmosphere like it did on Earth, in a sense that those collisions that hit the planet generated, when they exploded, generated the gas materials that basically went into it to form its atmosphere. And also the volcanoes on its surface also produces those gases, so namely the outgassing from the planet itself. So it has similar conditions to the Earth to produce atmosphere. It is also big enough in terms of mass to produce atmosphere and also retain it, at least for the most part. But then came a period where basically there was either probably, at this point it's speculation, there was an impact, large impacts from different objects. Those impact, what they did, they triggered a volcanoes on the entire, basically a huge number of volcanoes on the planet. And those volcanoes started to produce more gases, basically carbon dioxide mainly, releasing it into the atmosphere. And carbon dioxide is a greenhouse gas. So what happened in this case, it traps more of the heat, evaporating the water, the oceans that Venus had, and H2O, which is the water, also is a greenhouse gas, meaning that it also helps in the process of increasing the temperature. So the process gets basically becomes exponential. That's why it becomes a runaway. So in a sense, in here, what we have, excuse me, somebody's probably, yeah, I'm in the lab, by the way. So basically, in this case, what we have a runaway gas, a greenhouse gas. So basically, a greenhouse effect. So at the end of the day, the temperature gets increased more and more until the entire planet lost all of its oceans to the atmosphere. The temperature increased further. The oxygen and the hydrogen inside the water broke because of the higher temperatures and high collisions and so on and so forth. So that basically led to oxygen recombining with the carbon and to form carbon dioxide, more of that greenhouse gases basically, and the lighter element, namely hydrogen, was released to the atmosphere. So this is the condition where we are in terms of the planet. So this is why something that like a greenhouse effect, like what we're going through right now, for example, the temperature on Earth is suffering from global warming. So we are in a similar condition at this point. I mean, according to a lot of studies, it's still we still probably could prevent it from becoming a runway. In a sense, we could probably reverse it, but we're going to reach a point where probably it becomes irreversible, where it's too late. Okay, and that is really why the Venus is really serves as a good subject for our study, because of this thing, because we really have to learn from its experience to avoid the non-turning point. Once you reach that point, no matter what you do, basically, it's too late. So that's really what the whole thing is, and that's where Venus ended up in. Could we terraform Venus? I don't know. It looks like it's really probably a much tougher task than terraforming probably Mars or even probably the Moon, because they're probably, I mean, you could probably build domes on the Moon and plant stuff in them and retain the oxygen in it, and also have enough energy to have plants grow, and then also even probably have protective shields against the radiation. But that planet in there, Venus, right now, is probably a much tougher thing in there. I mean, one of the things also that Venus, I mean, we have some indication on its surface in terms of basically the collisions and so on and so forth. One of the problems that Venus does also is rotation. It's been so slow right now on its surface. I mean, yes, the rotation drives the weather on Earth, but also other things. And here, the fact that you have those temperatures on the bottom that are extremely high, and the temperature on top. So this will cause the air to circulate. And this is not a small amount of air. This is a lot of air that circulates. And when they do, they get started and they probably will never stop. Okay, because you don't have any regulators, you don't have any things to regulate their motion. The wind on the planet goes with tremendous speeds too. So it's really extreme conditions, as I was saying, okay? The geology right now, basically, of the planet is most likely a lot different than that of the Earth in terms of, one of the biggest difference, of course, is the plate tectonics. It looks like it doesn't have any. So this is what's going on. There is energy that is, because Venus is the same size as the Earth for all practical purposes. So it has the same amount of heat that it retained from when it formed. And it's trying to get rid of that heat. And that's exactly what Earth did. And also, it has radioactive materials in its core, just like the Earth does. So it's producing its own heat, even if in the absence, when it runs out of that basically relic heat from when it formed. It's making more through the radioactive processes. It needs to get rid of it, just like Earth does. Well, Earth has things going for it. It can do volcanoes, and that's probably what ultimately Venus will have to do in that situation. Can do earthquakes also here on Earth. And the plates, when they move also, and where they go into the subduction, when one goes into the other, that's also other ways of getting rid of that excess heat. Well, the entire planet Venus is just one block, does not have plates. So it's going to build up and build up energy underneath, trying to get on it. And the only way it does is through eruptions, through volcanic activity. So that's another way for it to dissipate heat. In doing so, it generates more of those greenhouse gases, and it gets hotter again on the surface because of radiation coming from the sun. Okay, so that's basically some of the stuff. In terms of similarities, we think that Venus has similar structure like the Earth does in terms of a core, probably a liquid core, a solid core, and a mantle, and also a crust, but the crust is just one big thin thing, one big basically structure, not divided into different divisions. So this is basically in a nutshell what the story of this unit is and what Venus does. So this is how it looks like from outside. Okay, even with the most powerful telescopes, you're not going to have to penetrate its surface, to penetrate the atmosphere to look at its surface. Okay, so it rotates on this very slowly, basically around its own axis. Does about 243 days, but it does it in the opposite direction. Remember, everybody is going clockwise around the sun, and it is going clockwise also around the sun. Everybody is spinning. I'm not clockwise, counterclockwise. Why am I saying clockwise? Okay, they are all going. I have my coffee. I didn't drink it. Sorry, guys. Okay, so they are all going counterclockwise around the sun, and they are all spinning counterclockwise around their axis, with the exception of two. Okay. One of them is spinning basically on its side, and forget about that, that's Uranus, and the other one is actually spinning in the opposite direction. This one is going clockwise, okay, in the opposite direction than the rest of the other planets. And as we said before, the sun rises in the west and sets in the east, as opposed to that of the other stars, and it turns extremely slow on it. A day on Venus would take about 243 days. I want you to remember this number because there is a homework assignment next week that's going to be based on these numbers, and you really need to understand what's going on with it. Because the year on Venus is what, 225 days, and that is for Venus to go once around around the sun. But in the same time, the day is 243 Earth days. Well, then I would suppose that the day is longer than the year. That's not true. It's actually still, the day is less than the year because of the fact that it's spinning backward, that's all, okay? While it's going in the opposite direction. So it's going to catch itself in the other side before it goes in a full cycle. So this is basically one of the peculiarity of this planet. And it's extremely slowly rotating. It's the slowest planet among all the planets that rotate around their own axes. Also, Mercury is slow, but it's not that slow, okay? Just to give you an idea. So this is basically one of its problems. There is another also reason why probably the greenhouse effect also started to go very, very also terrible on this planet, and its temperature increase to this extreme, is because of the fact that also it's slightly closer to the sun than the Earth does, okay? So it enjoyed a little longer than Mars the conditions for habitability, but then the conditions start to deteriorate because as the sun grows older and older, actually it increases in size, okay? Becomes bigger and bigger. So that's probably why also that is a problem. And the other thing also, because it has an atmosphere, because you might ask, okay, what happened to Mercury? I mean, Mercury is not that terrible compared to Venus, and it's a lot closer to the sun. Well, Mercury does not have an atmosphere, so it doesn't retain all of that heat. So whatever comes in is basically released at the other side when it's when it's night. So that is basically the similarity. Whereas this thing will retain it for a long, long time. Okay. So the atmosphere is 100 times more massive than that of the Earth. The surface pressure is about 90. It's actually 92%, 92 the atmospheric pressure on Earth. And it's mainly carbon dioxide, 96.5. And it has thick clouds of sulfuric acid. So nitrines, sulfuric acid. And it's because it's so hot, actually, the sulfuric acid does not reach the surface. It doesn't flow on the surface to become like a liquid. Okay, so it evaporates before even reaching the ground. So lightning has been detected, but there is no rain. It's really these clouds that are rubbing against one another, so they release a lot of static electricity. And this is probably what we think happened to it. It had underwent a runaway greenhouse. Now, the thing with it is also there are modern studies that suggest that the planet was in not so worse conditions anywhere between 150 million years to about 500 million years ago. Okay. So it has vortices, has a lot of wind. And again, the wind, as I was saying in there, because of the extreme temperatures between the top and the bottom. So it's like you have your water basically plug trying to fall into. So that's basically what's going on in here. So you have a lot of basically wind driven by the gradient in temperature between the surface and the ground. But again, when it starts in here, it has to start in another one. It becomes more like a convection in the mantle on Earth. Okay. As I said before, we had the Russians had a lander in there. Okay, and these are the pictures that the lander took. The surface is baked to tremendous high temperatures. This is portions of the lander itself that you see in the teeth in here. And actually the lander itself actually did not really survive for that long. Okay. So the planet itself is subject to a lot of temperatures. It looks like a volcanic activity had been actually detected on the surface in there, okay? Or at least what looks like volcanic remnants of from volcanoes. We don't know right now because of the tremendous thick pressure, atmospheric pressure, a thick atmosphere that the planet has, that there are volcanoes, but probably if they are, we cannot see them. It's so much thick that probably whatever comes from them is just goes and is absorbed in that atmosphere, okay? This is the lowlands and highlands. I wish this was water though, and oceans, I'm in oceans. But most of the features on the surface are named after basically women, because the entire planet is named after a woman, with the exception of the mountains or the high regions in the northern, near the North Pole, basically, of the planet that are named after a Maxwell, called Maxwell months. And these are how do we have this picture in here? Using radar technology, basically, when we went through the thick atmosphere and basically you send the radar penetrates this thick atmosphere and bounces back off the solid surface. So this is basically how the surface looks like. So in one of the homework assignments from next week, you're going to be asked to basically estimate the amount of water basically that is on the planet. And based on that, you're going to see, if you spread it throughout the entire surface, how thick the atmosphere is going to, the water ocean is going to be. Because it's going to be an ocean basically. And you're wondering what happened to the continents. Wouldn't that be, well, for the most part, the planet is the same uniform, basically lowlands. So that's not going to be a major problem at all. So your estimates are going to be about 700-800 meters basically, which is less than even a kilometer, is not too bad. So, but that is an issue in here. The atmosphere, the oceans that the planet had, based on the amount of carbon dioxide that is actually in the atmosphere and the oxygen that is in the atmosphere. So the problem basically in the homework, what it does is it takes all the atmosphere in here and removes all of the oxygen from the carbon dioxide and becomes an oxygen. And you take that oxygen and combine it with hydrogen. So basically now you have water, okay? You have H2O. You're asking, where am I going to get the hydrogen from? That's a good question. We don't know. Okay, you're not actually terraforming the planet. You're just doing a problem where you're going to take all the carbon dioxide in the atmosphere basically and dispose of the carbon, put it on the surface if you want to as rocks or whatever you want to, and now take the oxygen and find the corresponding amount of hydrogen, and now you have water, and put the water on the surface and see the thickness of the ocean, then how thick it's going to be. It's not going to be as thick as the ocean of the Earth, okay, which is really amazing, because the entire planet will have about 700-800 meters, whereas in here on Earth, there are some points in the oceans that are as deep as 8, 10, 11 kilometers. So the oceans in here are much, much more, and the water on the Earth is much, much more than the water on Venus. Is that a good thing or is that a bad thing? I don't know, honestly, because I know this is part of the homework that you're going to be doing, and we're going to have that discussion. Could be good, maybe because the water is a good regulator of temperature, and also it absorbs carbon dioxide too, and it helps at least in reducing as water to help slow down the process of the greenhouse effect. But here is the bad news too. If the planet becomes hotter, you will have more water released in the atmosphere, which will make the greenhouse effect also goes a lot faster and far more devastating. So I don't know. Is it a good thing to have more water or less water? I don't know. So this is actually a good, interesting question. And but your problem, actually, all you're doing in this problem was taking all of the carbon dioxide and taking the oxygen off of it, because each molecule of carbon has carbon dioxide has two oxygens. You take one of those two oxygens and you make out of it a hydrogen, and then combine it with two hydrogen atoms, and you have water. And now you do the math and you will find that how much water you have, knowing the density of water, which is 1 kilogram per liter. Since you can find how much kilograms of water you can form out of that, then you can find how much volume of water you have. And you will need the surface area of a sphere. The surface area of a sphere is 4 pi times the square of the radius of the sphere. And in this case, the radius of the sphere is just the radius of Venus. And radius of Venus is almost that of the Earth, which is about 6,400 kilometers. So once you have these numbers, then you can find the surface area. And then you need to ask how much height in the water to make up that volume of the water, because once you have the entire volume of the water you have, and you would want to sprinkle it on the entire surface of the planet, then it's going to go on that surface plus a depth, and that becomes that volume. So from here you find that depth of the water. As I was saying, the answer should be less than a kilometer, about 700, 800 meters. Okay. That's how the problem is. It's like, for example, taking this bottle of water and instead of drinking it, spilling it on the floor, and or at least on a container, and making sure the container has a finite size in terms of area, and asking how high, how thick the water is going to be on that container. That's in a similar fashion, basically, what that problem is. So I'm hoping that you guys engage with this problem and all of your problems from the homework assignment, including the one that deals actually with the I would call it a resonance, but it's really not that much resonance. In other words, how often would Venus will give us the same face when we look at it, okay? It's not every year, once a year, but you can find it how often it's going to spin in order to give us the same face. And there is some sort of a also synchronization in here that needs to happen. All you have to do is just take the number, the day on Venus and its rotation, and as the Earth moves around the Sun, and you will see that there is a ratio of 5 to 1 in that case, okay? Almost 5 to 1, 4.99999 something, which is 5, okay? So that is the homework assignment. I know we're not doing the homework this week, so probably we'll have to dedicate more time to it next time when we meet to discuss these problems and understand how to do them, okay? I promise you guys that all of the homework problems in this class are of the type of finding ratios of numbers and comparing the ratios, and that's exactly what they are. When needed, for example, when you're trying to define the volume, I will tell you the formula for the volume and the area, for example, and things like that, so that you don't have to worry about it. And at the end of the day, just finding ratios and dividing numbers and multiplying numbers, okay? So here is the surface of the planet. It looks like it also has some features of impacts that are actually from the early bombardment stage. Again, and it also has some of these features that are unique to it. And that looks like, for example, this surface features in it looks like some sort of an outflow of lava in here. So this is This is, so it has volcanoes and it has lava flows on the planet. And it also has this emerging of planets. So this is one way of the planet of disposing of that excess energy inside of it, okay? So this is the planet itself. In terms of structure, as I was saying, we believe that it's similar to the Earth in terms of structure. So whatever is causing the heat in Earth, it must be the same, okay? So and it's the same silicate structure and iron, nickel. As a matter of fact, the density of the planet is slightly less than that of the Earth. As a matter of fact, it's even less than Mercury. So it's a little denser, less dense. So in terms of the numbers in here, you really have to work out the numbers so that you can match the density. The radius of the planet is 6,052 kilometers. Remember, the Earth is 6,400 kilometers. So it's slightly about what? 350 kilometers less, basically. Not even much, okay? Maybe 330 kilometers less, okay? In terms of diameter between the two of them, okay? So this is basically the size of the planets and the different structure in here. And again, this is based on speculation. We really don't have we don't have really, at least, unlike, for example, what we do and have a lander on Mars, namely InSight, that landed in 2017, that gives us studies on the Mars quakes. Here we don't have that. It's just based on models that we have for the planet. One of the things you notice in here is that the crust in here in this case is not broken into different plates like it's on Earth, okay? So we don't think that there is plate tectonics, and that's what causes these features in here where magma at the end is released, or volcanoes to cause the to get rid of that excess heat on the surface, okay? And this is the thing about the planet that we talked about in here. It's extremely slow on its axis, and it's going clockwise in its rotation, okay? So after 243 Earth days, it's going to be noon again, okay? So it's extremely slow in its motion. And you're thinking, wait a minute, why did not go full cycle and then came back to noon? Well, the fact that it's moving backward. And actually part of the homework is you're going to model this one also, and you're going to see it either using geometry, basically drawing several positions, and you will see it in there, or you use the ratios and the proportions and find the calculation. So it's really, you have an option in here in terms of how to try to argue for this thing, to argue for the planets and its shape and things like that. So I hope that this unit makes sense to you guys, okay? I know we don't have a lot of assignments this week, and it's by design actually, because we just came up from a big exam. So we still have that discussion. We have those things from last week also in terms of discussions. So we really need to do catch up on the other thing. And we have that big project that you guys are supposed to be working on until that was started about 2 weeks ago. We still have 2 more weeks to complete the assignments for it, namely the lunar observations. So you still have a lot of things to do. Next week, as I was saying, there will be this homework assignment in addition to other things that will pop up in terms of quizzes and other things. Sounds good? Okay, very good. Thank you, Susan. Okay, guys, so I'm going to stop the recording unless you guys have any question in here. And I will see some of you are actually going to be here in a few minutes to the lab. And others, I will see you guys who are not taking the lab. I will see you guys on Tuesday. Sounds like it's a good plan too. Okay. See you guys.